Hi, welcome to the second episode of the series From Classical Mechanics to Cold Atoms, where I do my best to give you some intuition on how to transition from the classical world to the quantum world using a single atom. Let's go. In the previous episode, we saw that the atom can be in one of the two regimes, the classical regime and the quantum regime, and the question was, how can we go from one to the other? Is there a key parameter that we can use to quantify in which regime we are? And the answer is yes, and that parameter is called the de Broglie thermal wavelength. The key point of this parameter is that we can go from one regime to the other in a rather continuous way by changing the temperature with the dependence shown here, and therefore the atom behaves as a particle or as a wave depending on the temperature that we're dealing with. So if, for example, we have a temperature of about 300 Kelvin, the de Broglie wavelength is very small and therefore the atom behaves as a particle. On the other extreme, when the temperature is close to the absolute minimum, then the atom behaves as a wave. We can gain some intuition by thinking that in the first case, the de Broglie wavelength is very short and therefore we can know the atom's position with high precision. Whereas in the latter, the extension of the wave function prohibits us from knowing the position of the atom with a high degree of certainty. On the other hand, considering that the kinetic energy and the velocity of the atom are related by the expression shown here, then we can conclude that by reducing the atom speed, we can reduce its temperature and therefore increase the de Broglie wavelength. This means that by slowing down the atom, we can go from the classical regime to the quantum regime. This can be achieved by using a technique called laser cooling, which is going to be the topic of the next episode.